From stone to wool. Sounds like science fiction, right? But here's the reality. The world cranks out over 8 billion square meters of mineral wool every single year. That's enough to insulate and soundproof millions of buildings. Ever wonder how chunks of rock, basically useless on their own, transform into one of the most effective insulation materials out there? Today, we're going inside the world's largest mineral wool factory to unlock the secrets behind this cutting-edge manufacturing process. About 1,000 years ago on the Hawaiian Islands, in the heart of the Pacific Ocean, something amazing happened. Streams of molten lava, stretched by the wind, formed thin fibers that wove together into a natural insulating blanket. According to legend, these were the hairs of the goddess Pele, torn from her head each time a volcano erupted. In the early 20th century, a group of scientists also discovered the extraordinary insulating properties of this volcanic material. And from this knowledge, rock wool was born. But to insulate millions of homes, Hawaii's lava alone wasn't enough. Humanity had to recreate the forces of nature through industrial processes. In the United States, states with large basalt deposits like North Carolina, Missouri, and Utah became the primary sources of raw material for large-scale rock wool production. To produce stone wool, the first thing you need is raw material, rock. The most common types are basalt and dolomite, hard minerals that can withstand high temperatures. At the Cardinal Aggregates open pit quarry in Ohio, USA, over 700,000 tons of stone are extracted annually. The first step is removing overburden with giant excavators. For every 10 feet of removed earth, about 1,600 tons of basaltic rock are uncovered. Next comes drilling and blasting. Powerful drill rigs cut through stone at nearly 5 feet per minute, creating a grid of boreholes. Then, 15 to 30 holes are carefully loaded with explosives. Under the supervision of blast engineers, each explosion releases 15 to 25,000 tons of raw stone. After crushing, the stone is delivered to the crushing plant, where massive blocks are ground down to pieces smaller than 10 inches. Each bucket is weighed electronically before being dumped into waiting trucks. On peak days, over 400 trucks leave the quarry, delivering 16 to 18,000 tons of stone daily to production facilities. From these very blocks, in the next stage of melting and spinning, the stone is transformed into millions of thin mineral fibers, the foundation of modern stone wool insulation for buildings. Heavy trucks loaded with basalt from the quarry roll into the plant's receiving zone, marking the beginning of a massive industrial journey. Uniform-sized stones head straight to the production line, while rough chunks and impurities continue along conveyors toward the crushers. Onto the dosing conveyor, alongside the basalt stones, glossy black coke particles are evenly distributed. Adding coke doesn't just provide intense heat for the furnace, it also regulates the chemical composition, helping the basalt melt faster and more uniformly. Next comes the melting stage. The basalt and coke mixture gets fed into a massive furnace where temperatures climb above 2,700 degrees Fahrenheit. Under this intense heat, everything dissolves into a glowing red stream of lava rich in silica, aluminum oxide, calcium oxide, and magnesium oxide, transforming into a thick liquid almost identical to volcanic magma. When the molten stream pours out, sparks fly in every direction, and workers in ceramic fiber suits and metal masks step forward to check working conditions. These furnaces run non-stop, 24/7, because shutting them down not only burns through massive amounts of energy to restart, but also shortens the lifespan of the refractory lining. From the furnace, a stream of glowing lava flows onto high-speed spinning wheels. When the molten material hits the rotating surface, it flies outward and stretches into fibers thinner than a human hair. At the same time, a stream of hot air follows the rotation, carrying the fibers outward and rapidly cooling them in the air, locking in their thin yet strong form. The result is a rain of mineral fibers that settles into a light, fluffy mat with remarkable heat resistance and sound-absorbing capabilities. Rock wool fibers are collected immediately after formation, carried by a stream of hot air, and laid down evenly on large rotating drums or wide conveyors. Layer by layer, the thin strands form a continuous blanket of mineral wool. Powerful fans and suction channels are precisely calibrated to distribute the fibers uniformly. At this stage, the material is still soft and fluffy, like a flowing sea of white fibers. The rock wool takes the shape of a block, but the initial fiber streams are only a few inches thick, so they need to be layered continuously. The rock wool stream moves forward to the layering stage, where fiber mats are stacked one on top of another to increase thickness. This process typically increases the depth of the sheet from a few inches to 8 to 12 inches, depending on its end use. After layering to the desired thickness, the mineral wool mat feeds into a massive system of roller presses. Here, even pressure is applied across the entire surface, compressing the loose fibers into a sheet with precise dimensions. At the same time, mechanical arms along the sides of the conveyor repeatedly press the edges, holding them tight and preventing the material from spreading outward. The result is a densely compressed block of mineral wool with a uniform thickness of 8 to 12 inches. Once the mineral wool block is tightly compressed and stabilized, it passes through a high-speed cutting system. Blades trim away the excess edges, creating straight, even sides that match the desired shape. Then, additional cutters slice the thick blanket into individual panels or blocks, each with identical dimensions. By the end of this stage, the mineral wool transforms from a loose mat into neatly formed insulation boards. Each block is cut into standard panels, typically measuring about 2 feet by 4 feet, with thickness ranging from a couple of inches for residential applications to nearly 12 inches for heavy industrial insulation. The stone wool boards are ready now, but they've got to pass one crucial stage: quality control. Part of this process involves checking their hardness, where pressure tests are applied to make sure the boards can withstand mechanical loads without losing their shape or density. And since mineral wool is both fireproof and insulating, a fire resistance test is mandatory. Here, they use a flamethrower that scorches the surface to temperatures of around 2200 degrees, while a person can sit right behind it reading a newspaper, feeling nothing. After inspection is complete, the stone wool insulation boards are carefully wrapped in heavy-duty plastic film, then loaded onto trucks and shipped out to construction sites.
Every year, over 150 million cubic meters of plywood are produced worldwide, enough to have a train of wagons loaded with these sheets circle the Earth at the equator several times. But how is an ordinary tree trunk turned into this unique material, used in furniture, construction, and even shipbuilding? What secrets does the process hide? Starting with spa treatments for logs and ending with a hot press where layers of wood are permanently bonded into a monolith. Watch until the end and you'll learn about the secret pencil that remains after production and why it too has its own value.
It all starts in the forest, where the best specimens are selected for plywood production. You need perfectly straight, cylindrical trunks without a large number of knots or defects, preferably from birch, alder, or pine. After delivery to the factory, the logs undergo the first and very important stage of preparation, hydrothermal treatment. They are submerged in giant pools of hot water, where they spend several hours and sometimes a whole day. This kind of spa for logs has a purely practical purpose. The hot water softens the wood, making it more plastic and pliable. Without this, further processing would be impossible. After the bath, the logs are fed to a line where their bark is stripped off. Special machines quickly and efficiently clean the trunk, leaving a smooth, light surface.
The heart of the entire plywood production process is the peeling lathe. This is where something incredible happens. The prepared log, clamped at both ends, begins to rotate at a huge speed around its axis. A long, razor-sharp knife is slowly brought towards it. As it cuts into the wood, it begins to peel off not shavings, but a continuous, seamless ribbon just 1 or 2 millimeters thick. It's like unrolling a giant roll of paper towels. The machine literally unrolls the trunk like a scroll of ancient papyrus, turning a three-dimensional cylinder into a flat, long ribbon. This ribbon is called veneer. The long sheet of veneer moves further down the conveyor, where giant clippers chop it into sheets of standard size. All that's left of the log is a thin central cylinder, the so-called pencil, which is then used for other purposes. Freshly made veneer contains a lot of moisture, which is an enemy of the strength of the future plywood. Therefore, the next mandatory stage is drying. The veneer sheets are fed into long, multi-tiered drying chambers. Inside them, as if on the shelves of a giant cabinet, the sheets slowly move on a conveyor while hot air intensely blows on them from all sides. In a few minutes, the damp and flexible sheets turn into light, slightly brittle, and perfectly dry blanks.
At this stage, the dried veneer sheets are sorted by quality. Then they pass through a glue spreading machine. Special rollers, dipped in a bath of synthetic glue, Apply a uniform, sticky film to one side of every other sheet. Next begins the process of forming the layup. A dry sheet of veneer is placed on a table, and on top of it, a sheet coated with glue. And here lies the main secret. Each subsequent sheet is laid so that the direction of its grain is perpendicular to the previous one. If the first sheet's grain runs lengthwise, then the second's runs crosswise, and the third's lengthwise again. This cross-grain structure is the key to plywood's strength. It paralyzes the wood's natural tendency to split and evenly distributes the load.
That's why plywood is equally strong in all directions. The number of layers in the layup is always odd, so that the structure is symmetrical. The formed layups of veneer are fed to the most powerful section of production, the hot press. This is a giant multi-story structure, between whose plates several dozen future plywood sheets are loaded simultaneously. With an enormous force reaching tens of kilograms per square centimeter, the plates compress the veneer layups. At the same time, the plates are heated to a temperature of 150 degrees Celsius. Under the influence of high pressure and temperature, the glue polymerizes, permanently bonding the layers into a single, incredibly strong monolith.
Hot sheets of plywood come out from under the press and are stacked for gradual cooling. After this, they undergo final processing. Powerful circular saws trim the edges, giving the sheets precise geometric dimensions. Then comes sanding. The sheets pass through sanding machines with endless abrasive belts, which make their surface perfectly smooth. After this, each sheet undergoes strict quality control. Inspectors check it for defects, delaminations, knots, or glue spots. Depending on the surface quality, the plywood is assigned a certain grade, and a marking is applied to it. The finished stacks of plywood are sent to the warehouse to later become part of furniture, houses, and ships.
The pencil that remains after peeling the veneer is a vivid example of how modern production strives for maximum waste-free efficiency. It is not waste, but a valuable raw material. If the cylinder is massive enough, it is sent to a sawing line, where it gets a second life in the form of lumber. Small boards and bars are cut from it, which are ideal for creating the invisible but strong frames for sofas and armchairs, legs for chairs, elements of children's beds, or wooden couches.
Every year, enough glass fiber rebar is produced worldwide to challenge the dominance of steel itself. This isn't science fiction, it's modern manufacturing. The world spends billions fighting rust, repairing bridges and car parks destroyed by corrosion. But there is a solution. A composite material that is twice as strong as steel, 4 times lighter, and simply does not know the meaning of the word rust. The market for this material is growing at 12% a year, and today you will see how hundreds of bobbins and a barrel of resin give birth to the building material of the future.
It all begins at one end of a vast workshop, in front of a structure that looks like a giant library for thread. It's called a creel. On a wall several meters high, hundreds, sometimes thousands of huge bobbins are mounted in neat rows. Wound onto each one is a fine glass thread, or roving. This isn't the glass from your windows. It's a special glass fiber
produced by melting glass and drawing it through microscopic holes. The result is a thread thinner than a human hair, but with incredible tensile strength. This will be the skeleton. From each of these hundreds of bobbins, a single separate thread is drawn, and they all converge into one thick, fluffy bundle.
This river of glass fiber now begins its journey. It passes through a system of guides and tensioners. Each of the thousands of threads must be held at exactly the same tension. If one thread sags while another is too tight, the load in the final product will be distributed unevenly, compromising its strength. The dry glass bundle is then slowly submerged in a bath filled with a thick, sticky, honey-like liquid. This is the polymer resin, the flesh that will be built upon the glass skeleton. It's a complex chemical cocktail. The base is typically a polyester, vinyl ester, or epoxy resin. To this, a hardener is added, a catalyst that will trigger a chemical reaction, turning the liquid into a solid plastic. Various additives can also be mixed in. Pigments for color, UV inhibitors to protect the rebar from sunlight, and fire retardants. The purpose of this bath is to impregnate every single tiny fiber. The bundle must be completely saturated in the resin, leaving no dry spots. Now heavy and soaked in sticky resin, the bundle emerges from the bath and heads towards the point of its creation, the forming die. This is the heart of the entire process. Imagine a thick steel plate with the perfectly round, polished hole, its diameter precisely matching that of the future rebar. The die is heated to a specific temperature. As the wet bundle is pulled into this hole, several things happen at once. First, the die acts like a press, squeezing out all excess resin. Second, it compacts all the glass fibers tightly together, forming a perfectly round rod. Third, the heat from the die initiates the first stage of the curing reaction. Emerging from the die, we can already see the familiar shape of a rebar, but it is still soft and vulnerable. So how does it get its famous ribbed surface? Immediately after the die, while the rod is still hot and pliable, a special glass fiber strand is wound around it. A thin resin-soaked thread is wrapped in a spiral around the surface of the rod, creating the textured pattern. The formed and wrapped rod now enters the longest part of the machine, the curing tunnel, or polymerization oven. This is a long chamber which can stretch for dozens of meters, where a high temperature, typically around 200 degrees Celsius, is maintained. Here, the final transformation occurs. This isn't just drying. Under the heat, the resin molecules begin to rapidly link together, forming a strong, rigid, three-dimensional grid. The liquid, sticky syrup turns into an exceptionally strong and hard composite material, permanently bonding millions of glass fibers into a single, monolithic rod. As the rebar moves slowly through this hot tunnel, it acquires its final, rock-hard strength. But what is pulling it through this long journey? At the end of the line sits a special pulling device. It typically consists of two caterpillar track mechanisms, like those on a tank, positioned one above the other. They gently, but very firmly, grip the finished solid rebar and pull it towards them at a constant, precisely controlled speed. It is this machine that provides the force to draw the glass fibers through the resin bath, the forming die, and the oven. The speed of this movement is one of the most critical parameters controlling the quality of the final product. And so, from the other end of this long production line, an endless, perfectly straight, hard and hot GFRP rod emerges. The final act is cutting. An automatic saw is mounted across the line. It synchronizes with the speed of the moving rebar, and at the right moment, it makes a quick forward dash, and with a sharp whiz, it cuts a standard length, for example 6 or 12 meters, from the continuous rod. It then returns to its starting position. The finished, still warm rebars roll onto a cooling table, after which they are collected into bundles, tied, and sent to the warehouse. And so, before our very eyes, thousands of fragile glass threads and a barrel of sticky liquid have journeyed through baths, presses, and ovens to become the lightweight yet incredibly strong building material of the future.
The market for glass fiber rebar isn't yet a giant like the steel market, but it is the boldest newcomer, rapidly gaining traction. The global market for this material is already valued in the hundreds of millions of dollars, with staggering forecasts. It's expected to grow by 10 to 12% annually. Now for the key features that are making the steel industry nervous. The first and most obvious is weight. GFRP rebar is roughly 4 times lighter than steel of the same diameter. Imagine a lorry. It can deliver 4 times more GFRP rebar in a single trip than it could steel.
On the construction site, 2 workers can easily carry entire coils of GFRP rods, whereas moving steel requires a crane. This represents a colossal saving in logistics and labor. Second is strength. And here, GFRP steps into the ring and knocks steel out in the first round. Its tensile strength is approximately twice that of standard steel rebar. This means that for some structures, a smaller diameter rebar can be used, saving even more on weight and volume. But the ultimate advantage, the true superpower of GFRP, is its war on rust. The main enemy of any reinforced concrete structure, from bridges to car parks, is not the load, it's rust. Water and salts penetrate through microcracks in the concrete, reach the steel rebar, and it begins to corrode. Rust expands in volume and literally bursts the concrete from within. And GFRP? It simply laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means the lifespan of the structure increases dramatically. A concrete structure reinforced with steel is designed for about 50 years. A structure with GFRP rebar can easily be designed for a lifespan of over 100 years.